Good morning, everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Senior Marketing Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled Challenges in Global Analysis of Riserless Intervention Systems. Before I get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, you can ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Mahesh Sonawane. Mahesh is a principal engineer with 2H Offshore in Houston and has over 14 years of experience in riser and conductor engineering. He is a licensed PE in the state of Texas and graduated from Texas A&M University in 2007 with a master's degree in mechanical engineering. Throughout his career, he has been involved with over 100 drilling and intervention riser studies, serving clients worldwide. So with that, I'm going to pass things over to Mahesh to get us started today.
Thanks, Victoria, for the kind introduction. I'm really excited to be talking about this subject today, and I really hope that everyone who is joining us will find this information very useful. So the objective of this presentation today is to provide a brief introduction to analysis of riserless well intervention systems. So what we'll do is go over typical analysis scope of work for this, because this is an analysis focused presentation, but we'll also look at some of the components that are involved in the riserless operations. And we also have a case study on recent projects and work that we have done. So we'll share some learnings and findings from that as well. So we'll start off with an introduction to riserless intervention. We'll look at different types of interventions, and then specifically focus on riserless intervention and what type of equipment and system level components are involved in this. Then we'll move on to different analysis types and the codes that are involved in the analysis of these systems. And then finally, the bulk of this presentation will look at the case study that we worked on and the interesting findings as well as conclusions from that. So well intervention is an important activity for any offshore well. It can be seen as a maintenance activity that you do to upkeep the performance of the well or do any repairs. So well intervention is basically your ability to enter a well safely with a well-controlled device and perform operations that are other than drilling. And depending on the operations that are going to be performed, intervention can be classified as light, medium, or heavy intervention. And light intervention is the riserless well intervention or wireline operations that we are going to focus on today. And it typically focuses on wireline operations like either logging, fishing for pulling out some tools, or doing some maintenance activity, or taking some readings on the well by use of sensors. It may also involve some type of subsea pumping or circulation of fluids from the well. Medium intervention, on the other hand, is typically your coil tubing type of operation done for well stimulation or a few other things like zone isolation or reperforating a well. And then finally, you have a heavy intervention, which can be looked at as a workover operation. So you can look at the differences in these three types of operation in this picture. So on the left side, you see light well intervention, which is the wireline operation. And typically this can be done by a small vessel. So the vessel required for this operation is not very high specification. It can be done from an offshore construction vessel or a small intervention rig. We've also seen that they can use, if you're in shallow water, you can use barges for doing these operations. And basically you have a wire line and some downlines run from the vessel that interface with a subsea intervention package. In the middle picture, you can see medium intervention that typically involves a small bore riser. This is typically a drill pipe riser, either between 5 to 7 inch of bore, and you have an intervention package subsea, and you also have a tensioning system from a tower on the surface. And finally, to the right, you have the heavy intervention, which typically involves drilling riser. So you have a drilling riser and a BOP package, and you can do much complex and heavy operations with this. You can even run a landing string or another riser inside of this, to either pull your tubings or do much more complex operations. So why riserless well intervention? The main benefit of this small lightweight riserless well intervention is that it's a very cost-effective solution because most of the time you need a small rig or a vessel of opportunity that can be used for this, which tend to have lower day rates. And the equipment involved is also things like your wire lines, coil tubings, umbilicals, which is a low cost rental equipment when you compare to typical offshore expenditure that you have on drilling and other activities. So we came across this case study published in Offshore magazine where they showed that typical cost of this intervention operation was around 6 million. But by doing that operation, they could see an improvement in production of around 3,000 barrels per day from the well. And just based on the calculations, they could see a net present value of around 30 million by doing this operation over a period of 3 years. So basically, the operation paid itself back in less than 3 months, and then you have this good increase in production from your well. So especially if you're in a low oil price environment where there's a lot of restrictions on operational expenditure, this can be a very cost-effective solution of boosting production from your wells. So moving on to the system itself. So this shows a layout of a typical or a riserless intervention system that we worked on. So what you can see is you have an offshore vessel and you have an intervention package which is deployed on top of your well. And then you have these different downlines from run from the vessel. In the intervention package subsea, you have these different components and they can vary based on the OEMs who are manufacturing it, but typically you would have a pressure control head, which is a sealing element that allows the wire line to move in and out without any leakage. Then you also have an upper and a lower lubricator package. This allows for shearing of the wire line if there's a need for that. And finally, you have a well control package at the bottom, which is a primary well barrier, and it can be used again to shear the wire line or the tool string or coil tubing. It also provides power to the subsea tree for performing different operations. On the line side, in the middle, the blue line you can see is a wire line which is run from the vessel, and it goes inside your intervention package through the pressure control head, and that's where you run your tool string. On the left of that, the purple line is an umbilical with an umbilical termination assembly at the bottom of it, and then a flying lead which goes from the UTA to the intervention package. And depending on the operation that is to be performed, like in this case, they needed to circulate some fluids and pump some fluids. So they had two coil tubings, which are these green lines suspended with clump weights at the bottom, and another flying lead going to the intervention package. And these were Black Eagle types of hoses with passive disconnectors in them. So this just shows a layout of a typical system, but this may not be the exact system because there can be variations of this. There can be more downlines or less depending on what the purpose of the operation is. So looking at analysis types and the scope of this work, typically what the first thing that you would do in this is come up with a configuration for the system. So on the previous picture you saw you had these number of downlines. So you need to come up with optimum parameters for them. So what should be the weight? What should be the clump weight? Do you need any buoyancies for your flying leads? How should they be spaced out with respective to the intervention package? How much slack you need in the system? So you need to optimize all these parameters in order to have a functional system. So that's the first step. Once you have that, the next thing you do is operability analysis that tells you what are the operating limits for doing these operations in terms of the allowable vessel offset, the current speeds in which this operation can be done, and also the wave heights. And you do that by looking at a number of response parameters like how much stroke do you get in the wire line? Is there enough headroom for the wire line to accommodate the heave and the motions from the rig? The MBRs for these different flexibles and hoses that you have in the system, and then also stresses in your structural components like the coil tubing. You also look at the drift off analysis to see what happens in case you lose power and how how fast the rig would drift away, and how much load it would put in the system. Uh, a weak point analysis, again, it's an important activity, but in this case, different from a riser analysis where you're trying to see what would fail on the well. Here, yeah, the objective is to come up with sizing for different passive disconnect systems. And I have a few slides on this, so I'll come back to this later. But basically, trying to come up with the loads at which different downlines would disconnect from the well. You also need to look at fatigue analysis of the coil tubing because the coil tubing is quite sensitive to environmental loads. And we also look at some installation analysis, both for the coil tubings and downlines, but also for doing your ROV operations. Uh, Looking at design codes, the main challenge I would say for analyzing of riserless well intervention system is that there's no dedicated published code which you can use. There are a couple of different codes which are under work. So there's API RP17G2. There's a committee working on that, and you also have the TR14, which is intervention riser analysis, a technical report which is being worked on. But until these codes are published, what you have to do is you look at different options that are already published. So you have API standard 17G, which is the governing code for intervention risers. You can use that, and also standard 2RD, which is again a global analysis for production risers. So you could use the guidance and methodologies in there for doing this analysis. And then you rely on other codes like 17J and 17E, which have guidance for umbilical and flexible analysis. So you do a combination of the global codes and also the component level codes to come up with a scope of work and also a design criteria and methodology for doing this analysis. So moving on to the case study. So we're looking at a well intervention campaign in Gulf of Mexico. The water depth for these wells that we looked at were in the range of 7,000 feet. They had a few different wells. And these operations were performed with using a DP3 type offshore construction rig. It's a small rig around 100 meters length. And they had a number of downlines, so 2 coil tubings, 1 wire line, and an umbilical for the control system. So, and for the umbilical, they had 2 options. One was the UT hanging, free hanging, as you see in this picture. And another option was to install the umbilical on a subsea mud mat and then run a flying lead from there. This shows a top view of the analysis model and how the layout of all these different downlines were. So you can see from the moon, you have the moon pool of the vessel, and you have the downline, which is the wire line, which is the blue dots shown at the center, which is run and interfaces with the intervention package. The umbilical itself was run from the side of the vessel, and then you had a flying lead which takes it towards the intervention package. And you also had we also had 2 coil tubings which are deployed from the moon pool, which are not shown in this picture, but you'll see it in the model. So you have these different lines which are run from different locations from the rig, and then they all converge at one point on the intervention package. So when you model this, this becomes a 3D problem, and you can see the different snapshots. On the left, you have the elevation view. So the yellow line over here is the umbilical with the umbilical termination assembly mounted on a subsea mat, and then you have a flying lead towards the intervention package. Here's the subsea intervention package located on the well, and then you have a wire line which is going through that. On the side, you can see the coil tubings, which are these green lines, and the purple lines are the flying leads or the black eagle hose with some slack in them, again connecting or interfacing with the intervention package. So just shows the complexity of the model, because you have these 5 different lines, which are 4 different lines which are run, and they are very low stiffness elements. So it can become quite interesting problem just to build the model and to make them converge and also run this analysis. So the first step, the next step that we do is the operability analysis. And for this, what we are doing is we're trying to establish the limits in terms of the vessel offsets, currents and waves in which these operations can be performed. So we look at vessel offset all the way up to 10% of water depth. So for 7,000 feet, that's 700 feet from your well center. We also looked at surface current speeds up to 4 knots and bottom current speeds of 2 knots because this particular field in Gulf of Mexico did have bottom currents. And then we're also looking at different types of waves. We also looked at current directions of coming from different directions with respect to these downlines. And the objective here is to run this load case matrix, different offsets times the currents times the waves, and then you come up with an operating limit or an envelope within which the system can operate safely based on the response parameters of these different lines and their design criteria. So here's one result from the operability analysis. So on this chart here plot you can see is what are the safe operating limits for this downline for this riserless system. So on the x-axis over here you have vessel offsets, and on the y-axis you have surface current speeds. And these different colors, they represent different bottom current speeds. And this analysis is done for a 95% non-exceedance wave, and we did similar work for different waves, but this is just one of the example. One interesting thing that you can see from here is if you offset the rig on the right side or in the positive offset direction, you see there's this connector which is the SCCC connector. Now this is a passive disconnect system, a passive disconnect mechanism in the system. So what it does is if you exceed 4,000 pounds in this connector, it automatically disconnects the line. And this is a part of the coil tubing system. So you can see at vessel offsets around 4%, you would exceed the load in this connector and you disconnect it. If you are looking at high surface current velocities, you tend to get a lot of sail in your wire line, and that pulls your tool string up and you run out of headspace on your tool string. And hence this operation is limited by the tool string headspace for higher current speeds. And if you offset the rig in the negative direction or on the upstream direction of the current, you start exceeding your coil tubing stresses. So it's just an interesting finding that there's no one component which tends to limit your operations. Just depending on the type of load you're applying, whether it's current or wave or the direction in which your vessel is moving, you can have different components driving your operating limits. This shows an example of a deployment analysis that we did. So because all these elements, your coil tubings, wire lines, umbilicals, they're low stiffness components and they have very light weights. They tend to have large displacement. So you may run into issues where they're clashing with the vessel structure for certain current speeds. And there could be a need for using guide wires or some guideline to install these components. So in this case, the plan was to deploy the pressure control head using the support from the coil tubing. So you can see one of these lines is the coil tubing, and the pressure control head is being deployed on a wire line, and there's a tether attached between the two as a guiding mechanism. So the objective of this work here was to determine how much length of the tether was required and how much forces you would see during this operation, and also how much combined deflection of the coil tubing and the pressure control you would see during this. So you can make judgments regarding the environments in which this operation can be performed, and also to determine the loads in the tether, so you could select the right configuration and right specification so that it does not damage during the operation. We're looking at an emergency disconnect mechanism for the downline. So if you're familiar with riser systems on drilling risers and intervention risers, they have an emergency disconnect mechanism where you hit a button on the rig, and you have a connector which can disconnect the LMRP from the BOP or your EDP from your LRP. For riserless system, there's no active disconnect mechanism, so they have to rely on passive disconnect. And typically, this is done by using the SCCC disconnect mechanism or some shear pins or a wire line. So the mechanisms are set such that once you exceed the load or a torque in these, you would achieve a disconnect. So in this case, we had the umbilical deployed, and in the flying lead of the umbilical, which you can see is the catenary shape, there was a line which was run in parallel to that, which is this green line over here. And the green line or the wire line was selected such that the length was shorter than the length of the flying lead. So in case of large deflections, the wire line can pick up loads and trigger a disconnect mechanism. So this just shows an example here. The wire line itself was connected to a valve which could be triggered at force of around 1200 pounds. So based on the properties of the wire line, which was a half-inch diameter and the stiffness, uh, we were able to select a length which was around 125 feet, such that it would disconnect at a vessel offset of 3%. That way you're not disconnecting the wire for small currents or small offsets. In case this wire line is shorter than intended, you would tend to disconnect this at regular intervals, and then you would have to have a ROE go and redo the connections. So having the correct length of this wire was important for them. And you can see the example over here, like you have different current speeds, 2 knots to 4 knots, and different vessel offsets. And this analysis shows you, like, for different combinations of offsets and current speeds, how much load is picked up by this wire line. And once it's becomes taut and starts picking up load, we sized it or specified a length for it so that you can trigger your disconnect at a predetermined offset. Next, I'll move a bit into coil tubing, which are part of riserless intervention. A lot of time you would have coil tubings used for circulation operations. And in our experience, we've seen is that the coil tubing tend to be the most limiting component for these operations. And the reason is that coil tubings are highly sensitive to the current profile that you apply as a load, also the operating pressures that are being used, and what design criteria is being selected. And I'll go into each of these parameters over the next few slides. But we were able to enhance the operability of the system by doing sensitivities on a lot of these parameters, and then come up with an optimized solution that showed much better operability for the coil tubing. So first example is the current profile that you select. So for this operation, if you use a low shear current profile, and by low shear current profile, what I mean is a current profile that does not die down pretty quickly. So you have a current which are quite strong throughout the depth of the water column. And in this case, what we saw was, for this type of current profile, the operations were limited to 1.5 knots of current speed if you had no wave loading on it, and just above 1 knot if you select a 95% non-exceedance wave. But when we looked at the data, if we do a probabilistic assessment, we see that the low shear profile, even though it's a conservative profile, it occurs for less than 0.5% of the time during the year. So we looked at a suggestion of using a mid-shear current profile, and these typically tend to be concentrated at the surface. They do go down a bit, but the data showed that this profile occurred for over 60% of the time when you had loop currents. And what this showed was, if you use a medium shear current profile, you could operate in current speeds up to 2 knots or slightly above 2 knots. And thus, just selecting the profile using a probabilistic assessment from the data available made a big difference in the amount of uptime they had for these operations. The next is the design criteria that you select. So you can use a safety factor of 1.5, which would limit your stresses in the coil tubing to 67%, or you could use 80%, considering it's an extreme operation. Now, you can see the benefits between the two plots. You can enhance your operability from 2 knots of surface current speed to 2.5 knots of about 2.5 knots of current speed. And one of the rationale behind using an extreme design criteria was because these were temporary operations, and secondly, your coil tubing anyway goes through a plastic deformation when you're reeling it and unreeling it on it. So it's not a riser, like a riser pipe, which is in an unstressed position for most of its time and sees stresses only when it's deployed for the operations. So just in agreement with the operator, we were able to at least show them that, if they went with an extreme design criteria, if these were temporary operations, they could operate in higher environments if they had to. And lastly, on coil tubing, it's very important to look at the fatigue life on the coil tubing because it's such a small diameter and such a flexible element. You tend to see a lot of fatigue damage on coil tubings for if you intend to operate for extended period. So on this plot, on the x-axis you have different wave heights, and on the y-axis you have fatigue life. And what you can see is if you're in wave heights under 5 feet, you have fatigue life over 100 days, even 1,000 days. But if you're in wave heights of say 10 feet, your fatigue life could be 1 day. So it's the fatigue life of the coil is decays exponentially with increasing wave height. So have to be wary of operations, the wave heights in which these operations can be performed. You always have the option of reeling in and reeling out the coil tubing and changing the fatigue hotspot and increasing the life that you get from the coil tubing. But it's a good information to have to look at fatigue for these systems. And moving into ROV operations analysis, a lot of these downline operations for the riserless system, they are supported by an ROV, whether it's to make up the connections for the flying leads or monitoring the systems or moving from one well to another. The ROVs can be quite useful. And we looked at an ROV jumper installation analysis. In this case, they wanted to deploy the jumper on the coil tubing, and at the end of it, you had a ROV which would move or displace the end of the jumper by about 500 feet. And they wanted to see how much loads the ROV would experience during these operations, because it had a limit of around 250 pounds of force that it could pull on these jumpers. So when we did the initial analysis, what we saw was that the loads in the ROV was seeing were much higher than its capacity, and the solution to overcome this problem was to install some buoyancy modules on the jumper during the installation operation. And once the installation is done, they would remove these buoyancy modules. And the thing they were looking at was how many buoyancy modules were required and how they needed to be spaced out for this operation. So we did this simulation. This is a video. I hope this works. So what we can do we did in the simulation is simulate the motion of the ROV pulling the end of the jumper and making the connection with the intervention package. And we did this with different buoyancy modules. And we also looked at different speeds at which the ROV is moving, and we also looked at different bottom current speeds that the ROV can encounter. And based on that, came up with this table which shows that if you have different buoyancy modules, how the forces that the ROV sees in the horizontal and vertical direction can change. And this gave them good information that if they used around 8 buoyancy modules, they could get the total force to less than the capacity of the ROV. So this was an information that they were able to use for their operations. All right, so that brings me towards the end of my presentation, and to summarize it all, I would say is the key finding or the key takeaway from this is that the operating limits for riserless systems can be fairly limited, especially if you compare it with typical riser systems. Typical drilling riser or intervention risers, they can operate in 1-year winter storm or even stay connected in a 10-year winter storm. But the riserless well intervention, you can see issues in wave heights anything above 8 or 9 feet of wave heights and currents above 2 knots. And the main reason is that the coil tubing is one of the main limiting factors is the coil tubing, both in terms of its strength and fatigue capacity. Secondly, the second reason is that all of this equipment is lightweight equipment and is quite susceptible to environmental loads. And lastly, a lot of these operations typically are performed using a small intervention rig, which tends to have much higher motions compared to a Modu rig or a drill ship, which is quite stable. So just because these components are lightweight and because they tend to move a lot, you see a lot higher bending loads, and that tends to limit your operations. Secondly, there's no one given component that you can say it's the wireline or coil tubing that would drive the limit. So it's important that you look at it holistically, like like if you have all these different systems modeled in the model, you can look at the interaction between them and also come up, also see what is driving your operating parameters or operating limits. Uh, Another thing to keep in mind is because there's lack of design codes, it's important to select a design criteria as well as analysis parameters carefully in the beginning of the project. Selecting the exact or the right design pressure or the right parameters in which these operations will be performed can help in avoiding being over conservative in your assumptions, which tend to show that these operations may not be feasible. And finally, the global riser analysis, when you look at it, it turns out to be a quite useful tool, mainly if you're looking to optimize the system. Where it comes in handy is in terms of rating the equipment and sizing it. Like if you're having disconnect mechanisms like shear pins or your SCCC connectors, knowing at what point they will disconnect in field. And in order to prevent an accidental disconnect, if you don't select the right specification, if it's too weak, you might get a disconnect in your system when you don't intend to have one. So just the optimization process can help improve the uptime and be quite beneficial in terms of providing operational information that can be handy during while performing these operations in field. With that, that's the end of the presentation, and I'm happy to take any questions that you may have.
Thank you, Mahesh. That was great. Yeah, we'll just dive right into the questions. Okay, let me see. The first one is, does the analysis assume the vessel heading is fixed, i.e. not weather vaning?
No, we do consider weather vaning. So the assumption is that the vessel would maintain a 10 to 15 degree heading with respect to the waves. And we do, I didn't talk about it, but we do a directional analysis, and we also look at a vessel rotation to see if these lines tend to get entangled, or is there a limit up to which the vessel can rotate. So I think it's a good question, and we did look at some of that.
Okay, great. Thank you. Next question. Did you say the CT is in plastic deformation during reeling?
Right. So the coil tubing, because you're reeling it and reeling out, you tend to see a lot higher strain in the coil tubing. So you're definitely not less than your 100% or less than say 67% that you're trying to maintain for your global analysis. It tends to go into plastic deformation, and you do there's a limit of how many reel-ins and reel-outs you could do based on data.
Okay, thank you. Next one. What is the advantages of a riserless compared to a riser intervention?
Okay. I would say the main benefit is the cost, because there are two different things. You cannot do the same things that you can do with a riser system. The Riserless has its own application, but yeah, the main benefit I would say is that it's a cost-effective solution, and mainly used when there's not when not not heavy intervention operations are required. Just something that a wireline can do.
Okay, next question. Which software is used for conducting analysis of the riserless intervention system?
There are a variety of software that you can use. We use both Flexcom and OrcaFlex for these systems. OrcaFlex tend to behave much better for this analysis because I would say it handles flexible lines and down lines quite well compared to Flexcom. But we've done this in both software, and if you need, you can even do this in ANSYS or Abacus. So there's no predetermined software that you need for this.
Okay, thank you. Next one is, do you also perform interference analysis between the various lines, and is it a critical factor?
We did do look at interference analysis for these. I would say they tend to be spaced out quite well, where they do not. We like, at least on the project that we worked on, they didn't seem to have a clashing issues. The main issue that you see really is the lines getting entangled around the wire line, because you have a wire line going through the center. So if you select a current direction such that the umbilical is displacing towards the wire line, you can have a scenario where it starts touching. But a lot of this can be mitigated by weather vaning the rig and choosing such that the lines deflect away from the wire line.
Okay, thank you. Next one, how do you add up low and high cycle, how do you add up low and high cycle fatigue for coiled tubing?
So yeah, there's a published paper literature. It's by Schlumberger, one of the OEMs who are experts in coil tubing. So we use power law to combine the low cycle and high cycle fatigue. So for every deployment, so once you do that, you see for every subsequent deployment, you tend to get exponential or a reduced fatigue life. But again, that's assuming that the fatigue hotspot is the same. So on these coil tubings, if it's deployed from a sheave or if it's deployed from an injector, the point where the coil tubing comes out or it's deployed, that is the fatigue hotspot. The fatigue life in the rest of the coil tubing is not a problem. So if the fatigue hotspot stays the same, yeah, you can use the power law to combine the high and low cycle fatigue and see how it decays. But most of the time, because you're in different water depths and you won't have the same location. I mean, it can happen, but there are ways of monitoring what location of the coil tubing was in the fatigue hotspot and avoid it. That way you don't have to worry about the combining them.
Okay, thanks. We have another one. Any ideas on technology gaps, if any, for deeper WD riserless intervention cases?
I wouldn't say, because we have looked at 7,000 feet. We've also looked at 9,000 feet. I wouldn't say there's a technical gap as such, but my main observation is that the operating limits for these systems are quite limited. So one thing that we are looking at with one of the operators that we have worked on is how to improve the coil tubing fatigue, not just fatigue, both strength and fatigue performance. So because the coil tubing was deployed from an injector and you have a hard boundary condition over there, we're trying to see if we could improve the modeling in that location. Things like, can we model the rollers? Can we determine the compliance of that system? And we are talking about that. We haven't done one for HPHT systems, so I don't know if how developed these systems are for HPHT, but that could be something. But no, I'm not aware if there's a gap on the HPHT side.
Okay, great. I think let's do one or two more. What data is required to conduct this analysis, and how do you deal with lack of any well or environment specific information?
Okay. Yeah, so you need the data sheets for all your downlines, so your wire lines, umbilicals, coil tubing. So you need the specification, you also need the rig information and other offshore analysis information like metocean data. Soil is not that important, but if you have, it's good. In terms of lack of data, like if it's for Gulf of Mexico, there is published API documents which gives guidance on what data to use. And if not, you could always, we tend to leverage our in-house database. If you're in fields where there's no data, we can come up with some assumption or reasonable assumptions.
Okay, let's see. Okay, we'll do one more. On one slide, you showed fatigue life of coiled tubing is very low. How are these operations possible with such low fatigue life?
Right. So one thing, the coil tubing fatigue life is low, but I think as I've said before, the fatigue life is low only at that one location or a finite length where the coil tubing is deployed on the sheave or it's coming out of the injector. So one thing that you could do is if you have a 15-day operation and the fatigue life is only say 5 days, every couple of days you could reel in or reel out the coil tubing and put a different section of the uh, coil tubing at that fatigue hotspot and just manage the fatigue in the coil tubing. And you can, for that, you need to do some optimization, like how much slack you have in your flying leads at the subsea. That determines how much reel in and reel out you can do. So if you plan for that in advance, you can manage the fatigue life of the coil tubing.
Okay, we're just going to squeeze in one more question, and then I promise that's it. Can you use thermoplastics composite pipe as your coil tubing to alleviate fatigue concerns?
Yeah, I think that's a good solution. The composite pipes, thermoplastic, I think they have really good fatigue performance. Uh, I, I I personally think it might be a cost issue though. Like I don't know. I'm not expert in the cost of flexible lines, but they tend to be quite expensive. So, and I think coil tubing is a more cost effective solution. So, especially in this case, like the work that we did, uh, they had 7,000 feet of depth. So a lot of it was coil tubing, and at the end of that, they had the jumper, which I talked about. It was a composite jumper, so they were okay to buy that small piece of composite, but they didn't want to spend a lot on the entire 7,000 feet length. So it could definitely be a very useful solution, but I don't know how cost prohibitive it might be.
Okay, thank you so much. And yeah, Mahesh, thank you so much for all the information on the topic and answering all the questions. That's all the time that we have for today. But as we mentioned earlier, if you come up with any more questions or you'd like to continue this discussion, you can contact Mahesh directly using the details provided here. Thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening once a month, basically now in 2022. This is our last one for this year. You can check out the 2H website and LinkedIn for more details and to sign up. Again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. Thank you.